Welcome to AI Explains. Today we're diving into what sounds like an impossible mission. I mean, how do you take a picture of something that is, by its very nature, invisible?
Right, a black hole. The whole deal with the black hole is that its gravity is so strong not even light can get out.
Exactly. So a normal camera would just see nothing. A black spot in a black sky.
It's a real head-scratcher. You're trying to photograph a shadow in a pitch-black room.
But that's the trick, isn't it? We weren't looking for the hole itself. We were looking for its silhouette.
The theory was that if you have enough hot, glowing gas swirling around it,
Like water going down a drain.
exactly like that, the gravity should carve out this dark shadow right in the middle of all that light.
But the scale of this is just, it's hard to wrap your head around. The target, M87, is 55 million light years away.
Yeah, to give you a sense of that, trying to see it from Earth is like standing in New York and trying to read the date on a quarter.
A quarter in Los Angeles.
Quarter in Los Angeles.
A quarter?
It's an impossibly small target.
So your normal telescope, even a giant one like Hubble, just isn't going to cut it. Not even close.
No. For that kind of resolution, you'd need a lens. Well, you need a lens the size of planet Earth.
Which, is a bit of a construction challenge, so they had to hack it.
And this is where they got really, really clever. They used something called the Event Horizon Telescope.
Which isn't one telescope, it's a whole network.
It's 8 radio telescopes, scattered all over the globe. We're talking Hawaii, Chile, Spain, even Antarctica.
And they had to link them all together.
Perfectly. They used atomic clocks to sync every single telescope down to the nanosecond.
That's the key, right? The clocks.
Yeah.
So they could record the radio waves at the exact same instant from all these different spots.
And then they could stitch all that data together computationally to simulate that one giant Earth-sized eye.
And the amount of data they collected was just staggering. I heard the internet wasn't even fast enough to send it.
Oh, not even close. We're talking about 5 petabytes. 5,000 hard drives worth of data.
So what did they do?
They had to physically fly the hard drives, pulled them out, put them on planes, and flew them to supercomputers in Germany and the US.
The ultimate sneaker net.
It really was.
So after all that, they crunched this mountain of data, and what comes out is this image we've all seen now. That kind of blurry, glowing orange donut.
And that orange glow, that's not fire. That's plasma, superheated gas whipping around the black hole at billions of degrees.
And the dark patch in the middle. That's it. That's the main event.
That is the shadow of the black hole. That's the event horizon, the point of no return. Seeing that darkness is the proof that the black hole is really there.
Okay, but the thing that jumped out at me is that it's lopsided. The ring is way brighter on the bottom. Is that a glitch?
No, not at all. That's actually more proof. It's something called relativistic beaming.
Okay, break that down for me.
That gas is spinning at nearly the speed of light. The stuff at the bottom of the ring is moving toward us. So its light gets boosted, it gets brighter, it's like a headlight coming straight at you. The gas at the top is moving away, so it looks dimmer.
Wow. So just by looking at the brightness, you can tell which way it's spinning.
Precisely.
But here's the question. When you're building an image from all these scattered bits of data, how do you know you didn't just kind of create the image you expected to see? Human bias.
That was the team's biggest fear, and they had a brilliant solution for it.
What they do?
They split into 4 separate teams. They were completely isolated from each other. Different buildings, different algorithms. They couldn't share anything.
And they gave all 4 teams the exact same raw data.
The exact same data, and told them, okay, build the picture.
They all came back with the same thing.
They all came back with the same lopsided donut. That was the moment. That's when they knew it was real.
It's like 4 artists painting a portrait of someone they've never met without looking at each other's canvases.
Yeah.
And they all paint the same face.
Exactly. It proved the image was real, and it also proved that Einstein's math from 100 years ago, it holds up, even here.
So we did it. We turned the Earth into a giant camera and took a picture of this monster that's 6.5 billion times the mass of our sun.
We moved black holes from a theory on a chalkboard to a real physical thing we can see.
But now the Event Horizon Telescope is turning its eye to something closer to home, our own black hole, Sagittarius A.
And that's a much, much harder target.
Why? Isn't closer better?
It is, but M87 is a giant. The gas takes days or weeks to orbit it, so it basically sits still for the photo.
Why?
Sagittarius A is 1,000 times smaller. The gas whips around it in a matter of minutes.
So if M87 was like taking a still portrait of a mountain,
Yeah.
Sagittarius A is like trying to take a long exposure photo of a toddler who just had a box of candy. It's just going to be a
You get the
blur.
perfect analogy. It's going to be a blurry mess unless we figure out new ways to account for all that movement. We're going to need a video, not just a photo.
A challenge for the next deep dive, then. Thanks for listening to AI Explained.